In a revelation that's shaking the scientific world to its core, an advanced AI tool has uncovered something utterly astonishing hidden within the ancient images sent back by NASA's Voyager 2 spacecraft. The legendary probe that's been soaring through the cosmos for nearly half a century. This isn't just another routine update from the most distant human-made object ever to grace the stars. It's a discovery so bizarre, so mind-bending, that it's left astronomers, physicists, and space enthusiasts worldwide reeling with a mix of awe and disbelief. Voyager 2, launched in 1977, has been beaming back data from the edge of our solar system and beyond. But now, in 2025, a cutting-edge artificial intelligence has detected what appears to be a hidden message encoded in the grainy cosmic snapshots it captured decades ago. Is this a signal from an extraterrestrial intelligence, a glitch in the data, or something even stranger? The implications are staggering, and the excitement is palpable as experts scramble to decode what could be one of the greatest mysteries in space exploration history. Buckle up, because this journey into the unknown is about to take you on a roller coaster of wonder, speculation, and raw emotion that will leave you questioning everything we thought we knew about the universe. Let's rewind to the beginning, to a time when humanity's dreams of exploring the stars were just taking flight. On August 20th, 1977, a Titan III rocket roared into the sky from Cape Canaveral, carrying Voyager 2 on a mission that would redefine what we believed was possible. This was no ordinary spacecraft. It was part of NASA's audacious Grand Tour program, a once-in-a-lifetime opportunity to explore the outer planets, thanks to a rare alignment of Jupiter, Saturn, Uranus, and Neptune that wouldn't happen again for another 175 years. Voyager 2 was a marvel of engineering, packed with instruments to capture the secrets of distant worlds, a plasma detector to measure charged particles, a cosmic ray sensor to track high-energy radiation, a magnetometer to map magnetic fields, and an imaging science subsystem with narrow and wide-angle cameras to snap images that would captivate humanity for generations. It was built to last, with redundant systems to survive the brutal conditions of deep space, and powered by radioisotope thermoelectric generators, or RTG, that turn the heat from decaying plutonium-238 into electricity. These power sources were designed to keep the probe alive for decades, though their energy would slowly fade, forcing engineers to make tough choices about what to keep running as the years ticked by. The mission was ambitious from the start. Voyager 2's primary goal was to visit Jupiter and Saturn, with the possibility of extending its journey to Uranus and Neptune if it remained operational. But no one could have predicted just how far this plucky spacecraft would go, or the wonders it would uncover. Beyond its scientific instruments, Voyager 2 carried something profoundly symbolic. The Golden Record, a gold-plated copper disc etched with sounds, images, and greetings from Earth in multiple languages. It was a message in a bottle, cast into the cosmic ocean, a testament to humanity's hope that someone or something out there might one day find it. As Voyager 2 hurtled through space, its early months were spent calibrating instruments, testing its resilience against the harsh radiation and vacuum of interplanetary space. By 1978, the mission team was confident enough to prepare for its first major milestone, a close encounter with Jupiter. In 1979, Voyager 2 reached the gas giant, and the images it sent back were nothing short of breathtaking. Jupiter's swirling, multicolored cloud bands filled the frames, with the Great Red Spot, a storm larger than Earth, staring back like a cosmic eye. The probe's plasma instruments measured the chaotic space weather around the planet, while its magnetometer mapped a magnetic field so vast it stretched millions of kilometers into space. The moons of Jupiter, Io, Europa, Ganymede, and Callisto revealed worlds of their own, each with unique geological stories. Io stunned scientists with active volcanoes, the first ever observed beyond the Earth, spewing plumes of sulfur into space. Europa hinted at a subsurface ocean, a tantalizing clue to potential habitability. These discoveries were just the beginning, as Voyager 2 used Jupiter's gravity to slingshot toward its next target, Saturn. Arriving at Saturn in 1981, Voyager 2 continued to dazzle. Its cameras captured intricate details of the planet's iconic rings, revealing braided structure, subtle divisions, and mysterious features known as spokes, dark radial lines that baffled scientists. The magnetometer traced Saturn's magnetosphere, showing how it interacted with the solar wind, while observations of moons like Titan and Rhea added new layers to our understanding of the Saturnian system. Though its twin, Voyager 1, had already visited Saturn, Voyager 2's unique trajectory provided fresh perspectives, filling in gaps and offering a second look at regions missed by its sibling. But the real magic of Voyager 2's journey was yet to come, as it ventured into uncharted territory, the ice giants Uranus and Neptune. In 1986, Voyager 2 became the first and only spacecraft to visit Uranus, a planet tilted so dramatically on its axis that it rolls through space like a cosmic bowling ball. The probe revealed a magnetic field, strangely misaligned with the planet's rotation. Faint rings, barely visible against the backdrop of space, and a host of new moons, each with its own quirks. The data challenged everything scientists thought they knew about gas giants, showing that Uranus was a world of surprises. 3 years later, in 1989, Voyager 2 reached Neptune, capturing images of a deep blue planet with a massive storm dubbed the Great Dark Spot, a feature eerily similar to Jupiter's Great Red Spot but fleeting in comparison. Neptune's faint rings and its moon Triton, with its nitrogen geysers erupting into the frigid void, added to the mission's legacy. By the time Voyager 2 completed its flyby of Neptune, it had rewritten the textbooks on planetary science, proving that the outer solar system was a realm of dynamic, unpredictable beauty. With its planetary tour complete, Voyager 2's mission didn't end, it evolved. NASA shifted its focus to the extended mission, aiming to explore the heliosphere, the vast bubble of solar wind that surrounds our solar system. The cameras, having served their purpose, were powered down to conserve energy for other instruments like the plasma detector, cosmic ray sensor, and magnetometer. These tools were now tasked with studying the outer boundaries of the sun's influence, where the solar wind meets the interstellar medium. As the years passed, the RTG's power dwindled, forcing engineers to make heartbreaking decisions, shutting off heaters, cycling instruments, and prioritizing data collection over comfort. Yet Voyager 2 kept going, beaming back a steady stream of information about charged particles, magnetic fields, and plasma waves. By comparing its data with Voyager 1, which had taken a different path out of the solar system, scientists gained a three-dimensional view of the heliosphere's shape and behavior, revealing whether it was spherical, comet-like, or shaped by external galactic pressures. In November 2018, Voyager 2 achieved a monumental milestone. It crossed the heliopause, the boundary where the solar wind gives way to interstellar space. It became the second human-made object, after Voyager 1 in 2012, to enter this uncharted domain. The crossing was marked by dramatic shifts in the data. Plasma density spiked, the magnetic field realigned, and cosmic ray intensity surged as the probe left the sun's protective bubble. This moment was a triumph for astrophysics, offering a rare glimpse into the interface between our solar system and the galaxy beyond. The data showed that the heliopause wasn't uniform. Different regions appeared compressed or dynamic, possibly influenced by interstellar currents or magnetic interactions. Voyager 2's instruments, though limited by fading power, continued to send back invaluable readings, painting a picture of a boundary zone far more complex than anyone had imagined. But the story takes a jaw-dropping turn in 2024, when a team at NASA's Jet Propulsion Laboratory proposed a daring plan to reactivate Voyager 2's long-dormant cameras for one final imaging campaign. The idea was audacious. Those cameras, built in the 1970s, hadn't been used since the Neptune flyby in 1989. In interstellar space, far from the sun's light, capturing images was a gamble. The region was thought to be too dark, too faint, for the aging cameras to pick up anything meaningful. Plus, the RTGs were producing less power than ever, and turning on the cameras meant diverting energy from other critical systems. There were mechanical risks too. Shutters and filter wheels, untouched for decades, could jam or fail. Cosmic rays, more intense outside the heliosphere, could pepper the images with noise, turning them into static-filled messes. Yet the team believed that faint emissions from plasma interactions or dust at the heliopause might produce a glow just bright enough to detect. With advanced AI and quantum-assisted denoising techniques, they argued, even noisy images could reveal hidden structures. The plan was meticulous. Engineers spent months testing each component, sending commands to gently rotate filter wheels and warm the camera mechanisms to ensure they wouldn't seize. Every step was a nail-biter, with signals taking over 32 hours to travel round-trip between Earth and the spacecraft, now over 19 billion kilometers away. New software was uploaded to handle ultra-long exposures, some lasting up to 4 hours, while the spacecraft's orientation was carefully stabilized to avoid motion blur. Other instruments were dialed back to free up power, a delicate balancing act to keep the probe alive. In March 2025, the moment of truth arrived. The cameras powered on, shutters clicked, and Voyager 2 began capturing images of the heliopause, a region no camera had ever seen. The raw data trickled back to Earth at a glacial pace, each frame taking days to transmit. When the first images arrived in April 2025, they looked like chaos, speckled with bright spots and streaks from cosmic rays, a far cry from the vivid planetary portraits of decades past. But the team wasn't deterred. They knew the real magic would happen in the analysis. Enter the AI, a revolutionary tool trained on decades of space imagery, from Cassini's rings to Rosetta's comets. This wasn't your average algorithm. It was a deep learning powerhouse, capable of sifting through noise to find patterns invisible to the human eye. Working alongside a quantum-assisted filtering pipeline from the European Space Agency, the AI began processing the raw frames, stacking them to amplify faint signals and suppress random noise. Scientists cross-referenced the images with simultaneous data from Voyager 2's other instruments: cosmic ray spikes, plasma wave bursts, magnetic field shifts, to anchor their findings. What emerged was nothing short of astonishing. Filament-like structures, delicate and ghostly, stretching across the images. These weren't random artifacts. They appeared consistently across multiple frames, their positions and shapes correlating with bursts of particle activity and magnetic fluctuations. Some frames even hinted at geometric patterns, like faint hexagonal lattices or radial spokes, evoking the eerie symmetry of Saturn's polar hexagon, or the spokes in its rings. The scientific community erupted in a frenzy of speculation. Were these filaments magnetic field lines, twisted by the collision of solar and interstellar winds, glowing faintly as charged particles zipped along them? Or were they trails of interstellar dust, charged by cosmic rays and luminescing just enough to be captured by Voyager 2's cameras? Perhaps they were plasma waves, organizing into resonant patterns that shaped the boundary into visible structures. The correlations were tantalizing. When cosmic ray flux spiked, certain filaments brightened. When plasma waves oscillated, the patterns seemed to shift. The hexagonal shapes and spokes were even more perplexing. Could they be illusions from the camera's mechanics, like shutter timing errors or spin axis wobbles? Rigorous tests ruled out most hardware issues, as both NASA and ESA's independent analyses confirmed the pattern's consistency. Some scientists pointed to plasma instabilities, which can form repeating geometries in magnetized environments, while others dared to speculate about exotic physics. Could dark matter particles, like axions, be interacting with magnetic fields to produce faint photon emissions? The idea was a long shot, but the lack of a clear explanation kept it on the table. In mid-2025, NASA made a cautious announcement. Voyager 2's images suggested large-scale structures at the heliopause, but their nature remained unclear. The agency released preliminary findings in peer-reviewed journals, sparking a global wave of research. Universities and institutes worldwide jumped in, applying new denoising algorithms and running simulations to model the heliopause's dynamics. The patterns raised profound questions. If these were magnetic filaments, they could reveal how the sun's magnetic field tangles with the galaxies, shedding light on cosmic ray propagation and space weather. If dust was the culprit, it might point to unexpected concentrations of interstellar material, reshaping our understanding of the medium beyond our solar system. Plasma waves offered another compelling theory, suggesting the heliopause was a dynamic, vibrating boundary, organizing particles into intricate patterns. The hexagonal lattices and spokes, if real, hinted at self-organizing processes like those seen in planetary atmospheres or fluid dynamics, but on a cosmic scale. What made this discovery so emotional was its context. Voyager 2, a relic from an era of analog technology and slide rules, was still teaching us about the universe nearly 50 years after its launch. This tiny probe, built with 1970s tech, had outlived its creator's wildest dreams, surviving radiation, power shortages, and the vast emptiness of space to deliver a message from the edge of the solar system. The idea that it might have captured a hidden signal, whether from natural phenomena or something more profound, tugged at the heartstrings of anyone who's ever looked up at the stars and wondered if we're alone. The golden record, still aboard Voyager 2, was a reminder of humanity's hope to connect with the cosmos. Could these images be a response, a faint whisper from the universe, The possibility was slim, but it fueled imaginations and drove scientists to dig deeper. The discovery also highlighted the power of modern technology to breathe new life into old data. AI and quantum computing turned what looked like static into a window on the cosmos, proving that even decades-old instruments could reveal new truths with the right tools. This synergy between past and present sparked calls for future missions designed specifically for the heliopause, equipped with low-light cameras, advanced shielding, and real-time denoising software. Such a probe could map the boundary in high resolution, answering questions Voyager 2 could only hint at. For now, though, the aging spacecraft remains our only envoy in interstellar space. Every new image it captures is a precious gift, but each one comes at a cost. More power drained, more risk to its aging systems. Engineers are cautious about scheduling additional exposures, knowing the cameras could fail or the RTGs could finally give out. Yet, the allure of uncovering more secrets keeps the mission alive. The implications of Voyager 2's discovery ripple far beyond our solar system. If these filaments, hexagons, and spokes are real, they could be features of every star's boundary zone where stellar winds meet the interstellar medium. Observations of bow shocks around other stars or star-forming regions suggest similar structures might exist across the galaxy. If an alien civilization sent a probe to one of those stars, would it see the same patterns? The thought is thrilling, connecting Voyager 2's faint images to the broader tapestry of the cosmos. Closer to home, the findings could improve models of cosmic ray flux, helping us predict space weather and design better shielding for future missions to the Moon or Mars. The heliopause, once thought to be a simple boundary, is now revealed as a dynamic, structured frontier, alive with processes we're only beginning to understand. As the scientific community continues to analyze the data, the emotional weight of this discovery grows. Voyager 2's journey is a testament to human ingenuity, curiosity, and resilience. It's a reminder that even in the vast, cold darkness of space, there are stories waiting to be told. Stories that challenge our assumptions, ignite our imaginations, and pull us closer to the universe's mysteries. Whether these images hold a message from an alien intelligence, a glimpse of exotic physics, or simply a new view of our cosmic backyard, they've reignited a sense of wonder that spans generations. The heliopause is no longer just a boundary, it's a gateway to the unknown, and Voyager 2, against all odds, has given us a key. For now, the probe sails on, its instruments growing fainter, but its legacy burning brighter than ever. This is a story of exploration, of pushing beyond the limits of what we believe is possible, and it's a story that's far from over. Thanks for joining us on this incredible journey.